Welcome to the class. Today in the class, we are going to learn about heat of hydrogenation as well as heat of combustion. Usually the topic was so little, but as usual it is important also. First one, heat of hydrogenation. Usually we are having a question, what is meant by heat of hydrogenation? If I learn about thermodynamics, at the thermodynamics we are having different heat of reactions are there, enthalpies of reactions like heat of combustion, heat of neutralization, heat of atomization. Like this is also called as heat of hydrogenation. Means to a compound, if I am adding hydrogen to the compound, whatever may be the product form, the delta H, the heat that will be considered as the heat of hydrogenation. Means during the process of hydrogenation, addition of hydrogen to the compound, the heat evolved that will be considered to be heat of hydrogenation. So what will they ask in the examination? In objective examination, they can give 4 examples, 4 compounds, and they will ask which of the following compounds will have high heat of hydrogenation, which of the following compounds will have low heat of hydrogenation. Then obviously I'm having the question, sir, how can the compound has low heat of hydrogenation? How can the compound be has the high heat of hydrogenation? Then here in the example, in the introduction we are having, I am adding hydrogen to a compound. So high heat of hydrogenation, low heat of hydrogenation, that depends upon the stability of the compound given. Moreover, I know the stability of a compound is always been inversely proportional to the reactivity. Yeah, I know the inversely proportional. The more stable the compound must and should be, the low reactivity. The low reactivity, obviously, the low heat of hydrogenation, because the compound is not at all reacting, it is not at all evolving the heat of heat, obviously. So, a stability inversely proportional to reactivity here. So, high stable the compound, obviously compound will be low reactive, then it can evolve low heat of hydrogenation. Inverse also. So low stable the compound, high reactivity, high heat of hydrogenation. So in an examination, if compounds has been given and they're asking about the question which compound will have a high heat of hydrogenation and the low heat of hydrogenation, how to opt for the stability of the compound, whether the compound is high stable or low stable, then I had the question low heat of hydrogenation or high heat of hydrogenation. Okay, it is clear. But again I am having a problem. Sir, how can I go for the stability? Whether the given compound is low stable, whether the given compound is high stable, how can I know? Usually the heat of hydrogenation to the always we can go for a double bonded compound. An alkene or an alkyne, I will go hydrogen addition and I'm expecting the heat of hydrogenation. So here we are going for the stability of an alkene. As per the hyperconjugation, I know the aspects. For example, I am having a simple alkene like this and a alkene ring. Second example, the alkene is more substituted than the first alkene. More substituted means whatever the double bonded carbon will be there, that double bonded carbon atom surrounded by the more number of carbon atoms. Here, the double bonded carbon atoms are surrounded by only hydrogen atoms. As per the hyperconjugation, more number of alpha hydrogen atom, more stable the double bond will be. Here in the second example, we are having approximately alpha hydrogen atoms. 12 alpha hydrogen atoms are there. So 3, 3, 3, 3, 4 threes are 12. So I am having total 12 hyperconjugative structures. Nothing but the one sort of a resonance, more stable the alkene. Here in the first example, there are no alpha carbon atoms, no alpha hydrogen atom. So no resonance, no hyperconjugation. Then when I am comparing these two examples, sir, first example, heat of hydrogenation more, second example, heat of hydrogenation more, then obviously we can have a word from the above. The second example will be the highly stable so that it can have low heat of hydrogenation. First compound is low stable, so hence it is having high heat of hydrogenation. Obviously, the order is first compound will be greater than the second compound in terms of the heat of hydrogenation. Simple. So, in an examination, if an example has been given and high heat and low heat, if they ask, obviously I can go for the stability of the alkene, and the stability of alkene can be judged by the hyperconjugation, and the stability also been identified by the number of alpha hydrogen atoms. So, all put together summary, I'm having a word there. Around the double bond, more number of alpha hydrogens will be there. Obviously, the compound will have low heat of hydrogenation. Simple word. So, let us go for the some examples in which case the heat of hydrogenation more, in which case the heat of hydrogenation still should be less itself. Right. From the above, we had a version that any alkene which contains the more number of alpha hydrogens, that must be stable, compound must have low heat of hydrogenation. Keeping it in our mind, we are doing for the some examples. So first one. Example A, B, C, D. So there has been given out of the 4 compounds, which of the compound will have more heat of hydrogenation, which of the following compounds will have low heat of hydrogenation, and sometimes they will ask about the order also, increasing order, decreasing order, whatever. So first we can one by one all the compounds, as we have to go for the alpha hydrogen atom. Let us check how many alpha hydrogen atom can all the compound must and should be possess. So I'm rounding for the A example. This is the double bond and this is the alpha carbon atom one side and this is the alpha carbon atom other side. So one side alpha carbon atom 3 hydrogen, other side alpha carbon atom 1 hydrogen. So here total number of alpha hydrogens 4 alpha hydrogen. So option B. In this I am rounding the double bond. One side there are no alpha carbon atom, other side the alpha hydrogen atoms, total 2 alpha hydrogen atoms are there. 3. I am rounding the double bond here. One side there is no alpha hydrogen atom, another side CH3 will be there, other side CH2 will be there. So the alpha hydrogens, so total 5 alpha hydrogens. In the option D, I am rounding one side CH2, another side CH3, another side CH3. Obviously, number of alpha hydrogens is equal to 8 alpha hydrogen atoms. So, by comparing above, more number of alpha hydrogens, low heat. So, obviously, I am having. So, if they ask about the decreasing order of heat of hydrogenation, decreasing order means which compound will have more heat then least heat of hydrogenation. Option will be B greater than A greater than C greater than D, because less number of alpha hydrogen B possess 2. So high heat of hydrogenation. Then 4 A possess, then 5 C, then D. So more number of alpha hydrogens in the last case A, that alkene must be stable, that alkene will have a low heat of hydrogenation. Simple, sir. Okay, let us go for the another example for our clarity. A, this is B, C, and the D. So here also, let us check for the number of alpha hydrogen possessed, then we can decide which is having high heat of hydrogenation, which is having low heat of hydrogenation. Can you please do for it me? So when I round the carbon atom, one side there are no alpha hydrogen atom, another side I am having alpha hydrogen atom, there is also 1. When I round the carbon, one side there are no alpha hydrogen, this side 2 alpha hydrogen atom, 2 alpha hydrogen atoms, so total 4 here. When I round this compound, one side CH3, another side CH3, another side CH2, another side CH2. So total, obviously I am having 10 alpha hydrogen atom. If I round the compound, one side CH3, another side CH2, another side CH2. So total here alpha hydrogens is 7. First one we have a 1 alpha hydrogen. Then you got your answer. So A as contains low number of alpha hydrogen, high heat of hydrogenation. So obviously A, then B, then D, then C. This is the heat of hydrogenation in the decreasing order. Simple, sir. Similarly, for the second one, heat of combustion. Previously, we had heat of hydrogenation to the compound. When I am adding hydrogen, process is hydrogenation. The heat evolved, that can be called heat of hydrogenation. Similarly, here also to the compound, yeah, I know combustion. To the compound, when I am combusting, means when I am adding oxygen, whatever the products may be, the heat evolved, it can be called as heat of combustion. Here also the same version will be there, stability of the compound, everything, but extra one word will be there. More number of carbon atoms in a given compound, obviously the compound will have more heat of combustion. Along with the stability, here another word we have to, the compound which contains more number of carbon atom, the compound always have the more heat of combustion will be there. For example, I'm giving an examples. Option A. Sorry. B. This is option C. So they are asking about which of the compound will have more heat of combustion. But above, more number of carbon atom, more heat of combustion will be there. In the three examples, we are having CH3, CH2 common. Ethyl group is all. So go for the ring system. So here approximately there are 6, here approximately 5 carbon atoms, here approximately 1, 2, 3, 4, 5, 6, 7, 8 carbon atoms. So more number of carbon atom, more heat of combustion will be there. Obviously, C will have more carbon atom, more combustion will be the C, then A, then B. So in this way, by observing the number of carbon atom, we are going for the which compound will have more heat of combustion itself. For example, another one example we are going. So A, B, and obviously C. So we are going for the number of carbon atoms. So here total number of carbon atoms are 7 because 3 carbon atom present in the ring. Outside 4 carbon atoms are there, total 7. So this is a 5-membered ring. 5 carbon atoms in the ring. Outside 2, 7 carbon atom. It is a 6-membered ring. So 6 carbon atoms in the ring. Outside 1, 7 carbon atom. Hey, I am having a little bit of a doubt. Sir, in the above you said more number of carbon atom, more will be the heat of combustion. Then how can I solve this one? Because here all the compounds will have the same number of carbon atom. Then go for the stability. The first one we have to go for the number of carbon atom. Okay, above example that was clear, but the below example all the carbon atom will have the same. compounds will have the same number of carbon atom, then I have to go for the stability. These are the cyclic system, and I know in the cyclic system, stability of a cyclic system is always been 6-membered greater than 5-membered greater than 3-membered. And in the heat of hydrogenation, what we said, more stable, automatically it can have a low heat. So obviously in this example, when I am going for the order, which of the compound will have a high heat of combustion, low heat of combustion, the order is A will have high heat of combustion, then B, then C, because the stabilities are inversely proportional in the opposite direction. In this way, by having the number of carbon atom and the stabilities of the compounds, we can judge the compound will have high heat of hydrogenation and low heat of hydrogenation. Simple.